Good evening, ladies and gentlemen, colleagues, and fellow industry professionals. I'm 𝗥𝗲𝗍𝗆, Head of Training at HKIBIM. On behalf of the Institute and our co-organizer, the HKIE Building Division, I'm delighted to welcome you to tonight's technical sharing sessions. From concept to construction, navigate the design-build lifecycle in 3D. As the head of training, my goal is to ensure our members stay at the absolute forefront of digital construction and practical BIM application. However, before we dive into the technical list of the facade engineering, it is my honor to invite our moderator and the chairman of HKIBIM, Mr. 𝗥𝗲𝗍𝗆, and
First one, yes, the HKIE, the Building Division on Secretary.
Sorry, to share some opening for us. So, Perry, please.
Okay. Thank you all joining this very meaningful seminar today. So we have jointly organized by HKIBIM and our HKIE Building Division. So we have the seminar. The technical seminar title is BIM Technical Sharing. So the BIM expert here is the HKIBIM, the chairman, 𝗥𝗲𝗍𝗆, and Kevin. Later we'll introduce our speaker today, and we are shared with a very technical seminar today to present some latest development of the facade in the application of the BIM and help to the industry to speed up and enhance the accuracy and the efficiency of the construction. So now I pass the time to Juan to have to share some latest development of the BIM information to us and the members.
Sure. Thank you, Paris. Thank you for these opportunities. So just out of formality, I will do a quick introduction of HKIBIM. So this is a joint CBD event together with HKIE Building Divisions and HKIBIM. Okay, okay. So we are ready now. Okay, I'm chair for this term of HKIBIM. So thank you. Good evening, everyone, and the members of both institutes that join online and also on site. So HKIBIM, we are established in January 2009. Today we have around 1,500 members. So the objects to promote and advance BIMs, create general awareness in the industries, establish connections with the government bureaus and also tertiary educations and other institutes, providing guidance to on careers with our members. This is the new board established in 18th April 2025. So we have two vice chair for these terms, 𝗥𝗲𝗍𝗆 and also 𝗥𝗲𝗍𝗆. Public Services Committee. So just due to the expansion of the number of members right now, we for this term we have decided to set up a new community to help out with the board. So these are the 8 PSC Services Committee members. We have 14 corporate members to date. So these are all arranged in alphabetical orders. China division was an initiative set up last term. So today we have around 20 plus BIMers within GBA areas and also from Shanghai. Young membership divisions. This is divisions to recruit secondary school students. Some for Kowloon Sanyok Secondary School, they have already set up this BIM and GIS laboratory. So we are helping the young members. We are recruiting these young members, training the students in BIM and GIS. Today, these are all the CBD. So this is for this term we already completed 7. Past events, we completed the BIM Automation Arena 2025 first quarter of last year. So we have also arranged 3 site visits to Center of Future Construction of CIC, Trial T2, and then 𝗪𝗲𝗯𝗶 so 2 other CEDD projects. HKIBIM and KIBIM. So we have signed an MOU with Korean institutes of BIMs. So hopefully we'll be establishing other activities with these overseas BIM institutes. Our social medias, so stay tuned and try to follow us on all these social medias. Upcoming, so I'm going to just we are having a award dinner and ceremony on 17 April 2026 at Marriott Ocean Park. We'll be rolling out this GitHub to share some of these automations. So hopefully it will be out sometime within this year. Okay, I'll pass I'll pass it back to Kevin. Thank you, everyone.
Thank you, Guan, for those important updates. It is truly an exciting time for the Institute and our deepening partnership with the HKIE building divisions. So now, turning to our main program. To help us understand how we bridge the gap between the 3D concept and the physical landmark, we are privileged to have 2 experts from the 𝗪𝗲𝗯𝗶 retail. As many of you know, they are a global leader in custom facades for some of the world's most iconic luxury brands. Please join me in welcoming 𝗪𝗲𝗯𝗶H, Design Department Manager. Jose brings a wealth of the experience in managing the delicate transition from architectural intent to technical fabrication. And Stephen Kwok, a BIM expert. Stephen specializes in strategic modeling that ensures the geometric accuracy and structural integrity maintained throughout the whole entire 3D life cycle. They will be working with us through a landmark case study, tracing the full process from conceptual sketches to precise site installation. So now, Jose and Stephen, the floor is yours.
Hello, everybody. I'm going to share a presentation. Okay, let me share the other screen, not this one. Stop sharing. Share. Window. Should be the other one. Doesn't show. Okay, so we'll show this one.
This is good.
Yeah. Okay. Okay. So hello everybody. We are from 𝗪𝗪𝗯𝗶H Retail. So we specialize in facade. The whole company, 𝗪𝗪𝗯𝗶H, that does facade, curtain wall all over the world. But we belong to the business unit from retail. We do well-known projects in China, Asia, and around the world, and we are specializing in luxury retail brands. This is the context of what we do and what we use 3D in our design and build life cycle. So we are going to walk through normally which is the kind of project that we work on and how we integrate the progress in our projects. So normally when we start a project with one of our clients, for example, we will start from a concept or a project construction services. So before the tender is awarded and before the construction phase starts, we already start engaging them and we already start giving them support of which is the material limitation and other constructability issues. So in the life cycle of a project, we can start before even the tender and the construction phase starts. This is where a lot of the basic concepts on the 3D are still being already implemented and how we can get the maximum productivity of our 3D. In particularly, we are all around the world, but today we are going to show you one particular project that we finished in China. So because we are, our clients are luxury brands, and normally they like their privacy to be respected, I will simply show you a couple of images so you have an idea of the kind of the project. Okay, so this that you have here is a project in China, in Beijing. Is a 5-story building, a curtain wall unitized facade that on top of it we have a secondary decorative skin. This secondary decorative skin is the main part of the project. Although we were taking care of both parts of the building, of the whole envelope of the facade, mostly we will talk now about the 3D component that we had to go through from the concept creation to the completion. Okay, I will pass the rest of the presentation to Steven to go you through the work done.
Yes, hello everyone, this is Steven. Start. So I would like to talk about like how we basically walk through the whole 3D process. I think the kind of initial starting point is to receive the architect's model. And then based on like the real world constraints, site conditions, code requirements, some structural thinking at the initial point, and most importantly, to respect the architect's design intent to do our rationalization. So this is like the initial architect's model. Like they have an intent of, you can see on the left side, the blue is like some unique glasses. There's some repetitive kind of glass they want to do. Like basically they have a very complicated skin, but at the same time they want to save costs. So there's certain kind of parts that want to be repetitive and some parts that are unique to create this special skin. Once we get the model, we do some initial analysis. Maybe they are out of site boundaries, or maybe sometimes code requires some certain kind of maintenance zone. Initial kind of communication with factories. The glass sizes there's a certain constraints, and also sharp corners need to be avoided. So we do this kind of initial analysis, and we go through like the glasses are oversized in terms of what way. Okay. So then I think the very important part is to understand the design from our point of view. This is the PISA's first step. We need to establish our own way of modeling the design. And at the same time, we want to allow adaptation of various requirements that come along the way. For example, we have this kind of inner skin, right? So we have this kind of constraints when we want to set out our outer facade, actually, because we want most of the structural members supporting the facade to be perpendicular to the facade. So you can see the kind of initial idea is to understand the design, find a way to replicate how to model the design, but at the same time take care of the future constraints that is going to be imposed to the design. So with that in mind, actually we can establish our own way of creating the design, primarily in Rhino Grasshopper. We remodel the design, and then basically we can have a reiterative approach to gradually optimize the design so that we have minimum oversized glass. When there's a point where it cannot be optimized anymore, we are going to communicate with the architect whether they can adjust slightly the division of glass so that the glass can be within the boundaries. We also communicate them with the kind of sharp angles requirements so that we have a slight adjustment of the geometry. So you can see it's a very minimal geometry, but at the same time satisfying the requirement. So this is an initial architect service model, and this is like the PISA Gartner retail service model, before and after. So this is the kind of first stage of our modeling, which goes to the LD100. But at the same time, bearing in mind in future, there's some kind of fabrication and stuff. So this is like to also respect the kind of repetitive glass idea that the architect would like to have to save costs. So here we have 315 pieces of glass, we have 216 unique glasses, and the repetitive glass idea can be kept in the very first generation of LD100 model. So then we want to talk about the kind of wireframe development, which is a core process of every complex project we are doing here in 𝗪𝗪𝗃 Gardner Retail. No exception. That's no exceptions for this project because it allows us to do accurate engineering model and also based off this kind of true geometry information to develop further fabrication models. So we just go through the wireframe again. Firstly, we have this kind of the true curves that we get, the unique curves that are in red, and all the repetitive kind of glass representative curves. That will be the generation input that they get rotated 90 degrees, 180 degrees to ensure they are repetitive on 4 elevations. Basically, we want to show again, like these curves are not arbitrary. The adjustment also taking care of like the structural requirement, like the clearance, and also to maximize the kind of perpendicular element to the inner facade. Then we get the initial wireframe. From this wireframe, basically we start to get the kind of, the base geometry of the glass. You can see this is like the close boundary generate the glass. We take the architect division of glass, rotate it just like what we did, and then we get the surfaces. I think one of the key thing here is during the design process, we are thinking ahead, how this kind of things can be more economical and how this can be more realistic. So in here, like the pure generation of geometry may not be ideal because sometimes it gets really warpy or something. In here, trying to maximize the design intent while we can straighten all the edges to be straight so that in future, actually we have all the transoms are straight in the final fabrication models. And at the same time, you can see on the left bottom corner, there's a GIF and there's a straight transom models to show here we actually inform how the 2D is going to design.
Here, let me recap a little bit on, at the very beginning, the client provided a design surface. That is our starting point. After certain iterations, if we are thinking back on which stage of the project we are at the very beginnings of the stage, making sure that the limitation of the material can comply with the initial intent. And this is how the first initial iterations show, yes, we can achieve what you want. And this is how, with a small small variations, we can achieve that. Now, we go to the next level. We start modeling things already. And for example, here is a typical thing. 3D is never going to be the methodology by which we print a PDF and submit a 2D drawings. We need to do cuts. And do cuts that are going to be applied to a detail that is going to submit it. For a consultant, the architect, the government submission. What happened? And the bottom left image is a GIF too that you can see. When you have a really extreme geometry in a project, you can cut half a meter to the right of the same location that you were cutting before, and you get a different detail. But we cannot have hundreds of details. We need to always work and from the 3D get what is the one extreme of the equation. For example, in this case, how much is the glass going from in to out, so we can calculate the slope. We can have when the glass is vertical and when the glass is out to in. So you can measure the slope in the other direction. In this case, you only need to develop 3 details. One detail extreme in one direction, the middle, what everybody will call the typical one, and the other extreme. This is how the 3D is start generating 2D work. So there is not only a conversation with the architect, but the conversation with our system designer and our engineers.
I think this is the ethos of like this kind of project, this kind of complex project. We have 3 kind of details for each places so that we can cover everything, based on the code requirements and also, very easy to communicate with the architect. What's the dimension and stuff. Keep going. So at the end, we have this kind of, LD100 model of a glass. I think it's also one of the kind of decision-making process that we decided to have glass surfaces as a base object to carry forward, because I think one of the key things is also considering some kind of real-world situations that the lead time of the glass is the longest. We need almost 1 year to produce the glass. We cannot wait anymore. So at the end, we determined the glass to be the base object so that we have the naming system for the glasses. And then in Rhino, we input some kind of initial data so that we can keep going through that the glass is a parent and all the child will go inside like the brackets that we later will talk about. And which is a very productive kind of process that we think. Just like what Jose is saying, the extremities of the geometry determine how the 2D looks like and what's the kind of sealant joint, the gaps. At the end, it becomes very informative how the 2D is going to draw for the final submissions. Okay, so I think we want to talk about some kind of things that cannot be done without 3D or cannot be done without this kind of parametric modeling. So I think one of the trickiest part in this design is to locate the kind of brackets in the CHS. So basically, all the you can see on the left side. This is like a typical panel, glass, and they have different brackets. But each panel they share one CHS, so they are always competing for the space. So in here, I think computational design helps a lot because firstly we locate all the kind of corner brackets, and then basically using a kind of methodology like a kind of music chairs. So the first panel get the intermediate brackets space, and then the next one go to grab the remaining available space, and then the next one, and then the next one. They loop through like a music chair. So like at the end, all the brackets can be looped through the process without clashing each other. So it saves a lot of time, and I think it was one of the things that computational design can bring the efficiency in construction.
And another step related to this, if we see, for example, this project in the context of BD submission, in a BD submission, when we are doing any curtain wall submission, we will have to have a diagram of the maximum size of the panels with the setting out of the brackets normally for the typical and the worst condition. When we enter in this kind of project, every single panel becomes unique. The setting out of the brackets becomes unique. So it would be not practical, I would not say impossible, but it would be not practical that if we need to have this kind of setting out for every single kind of panel is drawn manually by CAD. Not only because it will take too long to draw, is that like the musical chair that Steven was saying, any future input where the client changes something or the engineering says, now this bracket doesn't work, you need to move it back, it will affect the next ones. This needs to be automated and needs to be scripted in a way that you can get the information fast.
Yes.
We are looking for efficiency here.
Yeah, and it can repeat, basically.
Yeah,
it can repeat. So once we talk about bracket in terms of points, then we basically locate them in space. So the left one is I think later we are going to talk about the engineering of the brackets. But each bracket, basically, you can see also there are some kind of attributes that is basically linked to the panel itself. So the child of the kind of parent panels. Then this kind of information is going to translate it directly to the engineering model that we directly talk about. But you can see on the right-hand side, like after the engineering model come back, we can directly transfer the calculated models and how the engineers assign the kind of bracket types directly mapped onto the brackets. And eventually it becomes the real bracket happening in the fabrication model. Which
to visualize when we say the engineering model and the input from the engineer, any panels is going to have a deadlock bracket, a horizontal slot hole, a vertical slot hole, and an oversized slot hole. This kind of information transfer between even within our own team, which is our own engineer and our own system designers, to pass this information. The tool to do this is an Excel file, which is an extraction from the 3D. So the engineer only says, this is the conditions that you need to meet, and here is the naming of every bracket for every condition. And automatically this information is transferred to the 3D.
Yes, so all the things have the naming. So for example, like the panel name and they have the bracket number, no, the panel number, and then the type of the bracket and whether it's left or right. So everything get connected to the base file. Once the engineering do like several rounds of updates, it can automatically update, and at the end the brackets are straight going to fabrication models. So this is like automatically fit into the carrier frame, basically the mullion and the transom.
Correct. That will be if we are not visualizing the 3D only as a model LOD 300 or 400. This has been the steps to where you go to a moment that the client is like, can you show me an LOD 300? Before we go to show you an LOD 300, we need to create all of these automations in advance. Yeah. Otherwise, what we are going to create is a dev model that when we change something, we have to manually change everything.
Yeah. So up till here, it is talking already about like 100 something files that interlink together, but it can be quickly updated one by one once their previous steps then need to be changed. Yes. So this is like the kind of panels that we talk about. Okay, so I think this sequence we are going from glass, to the frames that support it, and then to the CHS that is that the bracket is holding on. So inwards, going inwards. So we define the CHS basically just straight through the kind of geometry we talk about defined, using a very rigorous, just an offset relationship, determine all the intersections and create this kind of base surface, and then we get like the offset glass surface. Okay, so talking about the carrier frame model, I think one of the things is because we need to automate the geometries and the models. I mean, from panel to the carrier frame itself, it becomes there are a lot of types. So basically, here you can see the very very primitive diagram. We have a inverted triangle. A triangle that the point is pointing down, and that's a typical panel, and that the purple line is the kind of transom, and the light purple line is a mullion. So you can already see there are 3 base types, but you can see from the previous slides we have so many different segmented mullions. So all of them added together, we have numerous kind of types. So we need to have a rigorous filtering system to understand every kind of geometries and model them separately. And it can be automated in a certain way. And this gets translated directly to the engineering model that we talk about. And now here, you can see we have even defining the setting blocks for the carrier frame that the glass sit on. So this setting blocks is also related to whether a panel has transom or not, whether the mullion is segmented or not. And everything get automated in this way. So eventually we get into the panel engineering model. This engineering model is basically a very accurate model that represented the true geometry relationship with meshes, lines and points. This is one panel, and this is like the adjacent panels. And these panels, you can see this is like a line and point model, but it actually represented the kind of geometry information. For example, you can see there's a bracket in blue, very thin line. The purple, magenta is a mullion. The glass, various layers are meshes, triangles. Also, even the size setting block are represented in lines that is perfectly connected to the meshes, so that everything gets translated to the engineers for them to calculate. Of course, this demands a very expert engineering. It's an engineering feat, to be honest. So the engineer actually has a capability to master the parametric design, and understand like this kind of massive amount of data to make it possible. So eventually, like the glass and the panel calculation was done in Strand 7, but we can work together in a Rhino environment as well to have a live feedback, and we can go through like the kind of reiterative process that we talk about. Then, okay, we start to talk about the kind of CHS, 3 points in CHS. So CHS is a curved kind of structure that our bracket rests on. So I think the key thing we need to do is to make it single curved, the radius for easy manufacturing, which is very common. But there are three things in this project that is special. First thing is the curvature. So this is a very free-form curvature. So we want to also minimize the number of joints. So we're trying to best fit the kind of curvature into the free-form curve. So whenever the curve can fit a longer curve, we are going to do a longer radius. If it is too much, it's too much deviate from the original design, we need to go for a shorter curve. So that's the first thing we do in the automation model. Second thing is we want to avoid the joints we have a lot of different joints, like H-shaped joints, Y-shaped joints, K-shaped joints. We want the joints to be, the end point is not touching each other, because that cannot be welded together. So we always trying to have one end meet the meat of the kind of the curve. And the final thing is we want to avoid the brackets that we talk about, the 2,700 brackets. Because we haven't know at this point, this stage of modeling, which part we are going to divide to allow shipping, because we are still coordinating at that time, like how to divide the CHS to be shipped to the site for installation. So I think there's a lot of things that's going on for even modeling this kind of simple lines and points. So eventually it becomes a kind of geometries, having this kind of years that catches the ROS the next slide we'll be talking about. This slide is basically just talking about on the way we have some kind of very atypical situations that is common in many projects. So we need to develop custom tools. In this case, we are finding the best intersection of a very random looking years, because we need to raise the facade at the bottom level. That cannot be horizontal. Okay. Then we are talking about the kind of network of ROS that is behind the CHS. So we are going inwards and inwards. So here, I was talking to Jose for this presentation, so it's easier for us to understand this free-flowing glass surface is, of course, need to be supported somewhere. So this, at the end, is supported by this kind of rods, network system of rods that you can see on the right-hand side is a wireframe of the initial layout of ROS, and the left-hand side is a real build project. In here, you can see the curvature that we are trying to control is as 90 degrees as possible to make sure the efficiency of the ROS. As we said, in this kind of rod arrangement, we consider the kind of constraints of the inner curtain wall, embed locations, different kind of constraints, and just more structure. This is like the dead load, the sign color, the dead load cables, and then we have bracings and stuff. Okay, so within this network structure, how we are going to tie back the network of rods back to the main structure at the spandrel that we are seeing here. I think this comes to really the core of like a real communication between system designers, the facade designers, and 3D, because at that time we don't exactly know what's the result, but at the same time the system designers has to foresee what is going to happen. So basically we have different kinds of rods that meet each other. At the end, the system designer come with a facade solution that we have 4 main types of adaptive component brackets. So you can see on the top left corner, we have this kind of 4 main types. The first one basically is the adaptive component that takes care of the horizontal plane of the rods. So the rods that only comes back to the main building horizontally, use the first type. Second type is a horizontal plus the upwards rods. Third type, horizontal plane plus the downwards. Fourth is everything. So in here, you can see the system designer has a really smart design that can capture actually all the kind of directions of rods that goes back to the building. And how to determine the kind of how many quantity of the rod and how many types of rods and which and they go where is basically automatically determined by the 3D model, because the 3D model is already there, and you can basically analyze how they are coming from to that point. So through that, you automatically get how many types you are going to have during the design. So it counts for you, the 3D model. It does the work for you. So I think this is basically, you can see on the screenshot, is the kind of points, the center points of all the rods to that adaptive bracket we talk about. Also, you can see the little tiny legend on the top right corner. I think in this slide, before and after, just to show, again, the wireframe, the center line is exactly representing the fabrication model that we are going to see. And this becomes really effective because we actually, in this project, we take the fabrication model for client to have a final approval. And because it becomes really fast and automatic, so that we get, I think it was quite smooth during the process.
Yeah, because let's have a step back on the nitty-gritty details that Steven is explaining. All of this is really heavily visually impactful for what the client wants to see. The client wants to see a piece of glass that looks like a veil floating in there. Now we start doing engineering and we start showing them rods and tension cables and things like this. And they need to visualize and give us input. We have a VIP room here. This is too crowded, modify it. So we need to change, go to the engineer and come back. Again, at the S, and this is tied up with the name of the presentation, design and build life cycle through 3D. Because design is a process by which you keep going deeper on the spiral. You do one iteration, client, engineer, manufacturer, our system designer. You present to the client has comments. You do another loop, and you keep tightening, and you keep tightening, and you keep tightening, till the project, you run out of time, you run out of money, and everybody has done the best that they can do. Engineer has done the best they can do, 3D designer has done the best they can do, system designer, and the architect, you have walked through them with all the restraint. Architect and client, they know and have ownership of why the design end up being how it is. Yeah. So without a 3D in a complex geometry, this would not be possible. Or it would be hitting constantly against a wall because the client and the architect, they cannot visualize all the work that you are doing. Yeah. Because we are doing a presentation to you which looks like linear. We start with the glass, carrier frame, CHS, tension rod. But the reality is that we give a pass to everything. We get a comment and then we come back. We get a comment and then we come back. Again, was an iterative process.
No. Yeah, I would say without this kind of repetitive process or like this kind of system, it would take a century to finish, because I think it is really a lot of automation happening here. Same slide, center point, fabrication model, same relationship. Okay, we need to go fast. Final two parts for the 3D model, 3D modeling. I think talk about a little bit about the fabrication. So initially, behind this adaptive bracket, we have this kind of steel bracket tied to the main steel structure. Unfortunately, the site survey come back, and it is not ideal line as we all expected. But we can quickly talk to the site team, and we have a communication also through data sheet. Then they quickly come back with us each point, what is a site survey, and then we basically recreate the whole steel frame quickly, and then we just directly fabricate and send to the site, and we don't have any cutting on site for installing this kind of steel fabrication. Otherwise, we will have a lot of remedials on site, costing time and money. Adaptive components in front, same. Basically, depends on how the rods are hitting the kind of points. We automatically generate all types of brackets through computational design. all the rods have their own attributes and naming. This is the kind of diagram showing the actual installation diagram for the site installer to install. But at the same time, we can see we embed all the kind of information to our models.
Which, by the way, that is a tool, the same way that before we were talking about with the engineer and the system designer, how the engineering is explaining us which are the dead load brackets, which has the slot holes like this, which is the vertical slot. So this is a communication tool to our site teams and our manufacturer. They are getting a really digestible quantity of information. There were hundreds of rods. There were hundreds of brackets with a small different variation, but having a really clear color coding system, numbering system, and documents that they are really easy to read, the communication with the team becomes easy. And at the end, we are looking for efficiency. Efficiency on site, efficiency on the manufacturing.
Okay, so we talk about the CHS. So this is the final, shipping unit to the site that we can do. Okay, so this is like the kind of, in process 3D model that I think we want to show this slide because we want to show that during each stage, we actually create partial models for client to approve, to see the visuals of the details.
Correct, because what we were working 99% of our time was in that wireframe 3D that doesn't tell you anything if you are an architect. Doesn't give you a visualization, which is the final product. But we were able to bake through Rhino and extract this kind of, not an LOD 350 yet, not 400 for manufacturing, but they are in this 200, 250 that is good enough for them to give an approval. Modulation, size of the cappings, size of the glass, proportion.
The most important visual elements.
Yes.
Yes. So eventually we come through and we have a kind of full LD 400 models that is used for everything, fabrication, site installation, client's final approval for everything. Oh, okay. Final part for 3D modeling. As we said, all the models are linked with data. We have a lot of attributes in our objects in the 3D space. We link with the so for the first steel bracket, we link with the site survey data, for example, and what is the type of the bracket, and which it is connected to, where it is. The front adaptive component showing all the kind of, also the kind of node information, where it is, the angles, the position, base type, and the base mode it is. This is also data is also used through communication with the engineers. You can see this is the engineering data sheet that I communicate with our expert engineer. He automatically load through my engineering model and give all the kind of load cases utilization to the model. Once it is the utilization is high, it becomes another kind of sectional profiles. So that at the end we keep track of everything and it is correctly reflected in the model without manually doing it, because we are going to update through data sheets. And finally, I think not only within the design team, we are talking through data with project teams, QA, QC. We quickly export all the data for them to measure panels in the factory to make sure the things are in tolerance. Project team can make use of this table to input their preferred construction sequence. Coordinators can keep track of which glass has been done, has been shipped through one single table that we can keep referring to. Some kind of GIF to show some kind of, it looks improbable installation, but at the same time, because we have some signages in the CHS, it is already very tight space. And we have some signages that go through the CHS. We want to know whether the panel can be installed or not, so that we have a lot of this kind of animations.
This becomes, again, a tool of communication with our site installers where we show them which is the installation sequence. So this is a part of the method, the installation method.
Yeah, one more GIF. So basically, luxury brands are really, they want to expose their design at the very last minute to have the kind of wow effect. At that time, we need to install the canvas on top of our outer skin facade, which is already very optimized, so that we want to understand the load apply to the canvas, whether it's acceptable or not, what is the kind of support that we can apply to the canvas. And at the same time, client want to know this irregular facade, how the canvas is going to apply. So I think the animation and also the kind of this is also kind of actually an engineering model to let everyone knows how it is look like as a fabric on the kind of massing. Okay, so I think the conclusion, not the conclusion, but this is just the modeling part. We have few more slides, but I think few important things. Object-based, like a determination of things that model based on objects, so that everything can go afterwards. So in this case, it's a glass as an object. Second thing is like a downstream linear process, because I think, as Jose said, everything is that's so complex, but at the same time, there are many changes. We need to establish this kind of process that allow us to be adaptive in the process. And also, as we all know, doing this kind of grasshopper or scripting, it's easier to debug. If it is too long, it's very hard to debug, and it costs so many time. At the end, like this kind of consistent information data exchange between the teams is very helpful and productive between everyone. So we have some more slides about the real construction.
There are another utilities for the 3D. The 3D help us as well to extract information that can be used for manufacturing and QA/QC. For example, this one was one of an example. Every one of the brackets that we were showing before, they have different angles for the tension rods. What happened is that how difficult in a 3D shape is to measure the angle. So instead of asking the manufacturer, go and measure the angle for us, we simply cut a template from the 3D that has the perfect shape. So it's make sure that if this can fit within your bracket, it's within tolerances. If it doesn't, if you cannot make it fit, it's because it doesn't, it's out of tolerances. Every one of these brackets, they were cast. So it takes a long time to manufacture them and make sure that they are going to deliver on time within the correct tolerances. There were no time for too much back and forth between factory and site. This is an idea of how these CHS that we were talking look like. This is a 12-meter long CHS that has been manufactured all in one piece, and then later it will be cut to be sent on site. That was the color coding that Steven was showing previously. So the manufacturer already can know where he's going to cut a certain piece, so it fits within the truck and it can be lifted and installed on site. All of the CHS, because you have a 3D model, it can be 3D scanned, and you can have a color coding of where is your tolerances. So you establish a ±5 millimeters tolerances, and you find where is going to be your hotspot where the tolerances are out, and then the manufacturer can focus and try to rectify that parts. That was for the CHS, so the carrier frame. So the glass comes with 3 sides steel that holds the glass. That was this carrier frame. Every single piece was a completely unique shape. It's not cylindrical, it's not a conical, it was like an organic shape. So it required jigs and required this kind of 3D scans to make sure that they are within tolerances. Again, if you see how complex this geometry of one is, having certain control points and plus minus left right, it won't be enough information. This kind of heat map will show you hundreds of thousands of points within one frame, and to know which is the errors. The same for the glass. We were choosing which is the biggest glasses that they are going to be manufactured, which can be a trouble. They will be given to the manufacturer, and they use that information for fabrication drawings, and then later for measure every single glass. Unfortunately, when you have a glass, when you have a square glass, really easy. You measure the height, you measure the width, you measure the diagonal, easy peasy. When you have a 3D shaped triangular glass, how do you measure it? Because you cannot measure a diagonal. The glass is curved itself. So they were using a point, a 0, 0, 0 point on the space, and they were measuring for that point to every piece of glass. That only can happen if you have a 3D model of every single piece of glass. And the manufacturer is willing to work with you and use your raw data for them to measure. As well, not only for manufacturing approval, this is a communication tool with your installer. This is the color coding that I was showing before. What you were seeing that was laid out on the ground is this color code and how it's being delivered on site, packaged, and installed in that correct sequence. On site will be surveyed accordingly, and every single control point on the survey is going to be measured and feedback to know where you are within the tolerances. And the installation sequence of the glass, we were showing before, it's a CHS structure, which a pull and push rod system. It needs to be installed and loaded in a certain sequence. It cannot be all on one side and nothing on the other. So this is a really easy communication tool to others. As well, for approval of the architect, when we have a mock-up on site and when we have what we model, they can see that what they saw on the mock-up and what they see on site is exactly the same. Okay. So thank you so much for your time. That will be our presentation. I hope that we are trying to convey this message of from the day that the client approaches and propose an intent, and they give us a 3D sketch or initial render, they have something to start with till we end up building. We require, with this kind of geometries, we require a 3D. It gives us efficiency, it gives us accuracy, and most importantly, it improves the communication. So the client are more confident that they are getting what they are expecting, because they can see and they can walk with you the whole process. So from design to build life cycle.
Yes, thank you very much.
Thank you very much, Jose and Stephen. So I think wherever you're a seasoned manager, a BIM manager, or engineering looking to understand the latest facade technology, I'm confident that you find tonight's insight is invaluable. Following the presentations, we have the Q&A sections. For those online members, please feel free to type your question into the chat using the Q&A functions, or we can take the Q&As, the question from your guys. So maybe just start from my side first. Simple question first. So I think those shapes are so organic. Mm-hmm. So how big is the biggest glasses in this facade?
It's 5 meters by 2.4 meters by 350 mm depth. So this is the bounding box that we work with. So you can see in the initial stage, we basically fine-tuning all these kind of curves, and it automatically generated with the divisions, like the glass surface. So it's a live model. So once you adjust all the things within the boundaries and the constraints, at the end you achieve a model without the kind of boxes. That is rare, for example. Then you are okay. So this is a short answer. Because there is a constraint on the manufacturer, they should have a constraint of the biggest size. Yes. So you have to check with your manufacturer if they can match, right?
And in this particular project, it was not the typical limitation based on the raw material on the glass that the manufacturer gets, or even the autoclave where they temper the glass. In this case as well, we had a fritting. Yes. So the color, when you saw this image as an example, for example, of the mock-up, that you can see that the glass is blue-pink, that is a dichroic effect that is generated by a fritting that is on one side is dichroic color, but on the back it was white. So we're two fritting, one on top of each other, laser removed. Yeah. So that machine, how it cuts the fritting, that one is another limitation, not only the manufacturing of the glass itself.
Yeah, the glass could go a little bit bigger, but glass plus the frit is smaller, so the frit was the limit. Okay. Yeah.
Correct.
It was 5.5 times 2.4 meters. Yeah. Yes.
That's a pretty big one.
Yeah, that is why when the project is complex, we require one of the services that we are trying always to bring to our clients. Most of our clients that we do bigger projects, they understand this because we have collaborated for a while and they are used to this kind of process. But to be able to achieve, sometimes we don't even know that we started with a dichroic. Yeah. But we discover all of this along the project, but we require time to figure it out, which is the limitation. We need to have mock-ups. The client needs to be able to see against the light. It needs to be able, that is what we are looking for. All of that requires time. So we need to do always a pre-construction service where we go and try to nail down all of these initial constraints of the project before we enter in a construction phase where everything is be efficient, quick, no more design changes because that will delay the project and go over budget. So we try to spend all of the time and all the brain power to solve everything during design development.
This is one of the most sizable project in the pre-construction surface to the design build. So
yeah.
Cool. So guests and members. Yeah, sure.
So what do you think of the quality of the manufacturer of these glasses? Because so complicated and the quality of the glasses.
The quality right now in China is really high. 5-10 years ago, we still had the limitations that any complex geometry or any complex fitting, it has to be done in Europe and needs to be shipped, which requires normally a longer lead time, higher cost. Now China is able to manufacture this kind of glasses with a really good tolerances, more or less within a decent amount of time. And now you don't have to deal with shipping, now can be affected by the war or the prices of the oil, this kind of thing. So when you are working in projects in Asia, you can perfectly get all the raw material from China. They have the quality and the expertise.
I think those glasses are so free from, even though they are not in a regular shape. So did the factory directly take the 3D data from your side, or you still transfer from 2D? I don't think that is possible.
They use 3D because the way that we have not brought the video, but we didn't bring the video, right? No. So the way that they do it, the old school is that you have a mold. So they hit the glass and it slams. But now they have these machines that automatically have pistons and the glass rolls and it follows the shape. They require a 3D to be able to do that.
So you directly gave them the 3D?
Correct.
Okay.
Yes.
Correct.
Also for the SHS, also gave them directly the 3D.
Yes.
They are not kind of the quite free form, I think, right?
Yes.
Correct. And again, same that the question with the steel, they are really professional. They have a really good quality of manufacturing. They buy their machines to 3D scan. They work with us to find which is the limitation, how we are going to do the jig. We can find high quality manufacturers in China to do all of this.
Cool. Thank you. So I think we are running out of time. So let me just have the closing. Thank you very much, Jose and Stephen, for the masterclass in facade engineering tonight. It's clear that the journey from a 3D concept to a physical landmark require incredible technical precision and truly integrated BIM workflow. And thank you for our audience, both in here and the room and the online, for those engaging questions during the Q&A. To formally show our appreciation, I would like now to move on our souvenir presentation. I would like to invite our Chairman Guan and Paris to join me and our guest speaker in the front to present a small token of gratitude for their time and expertise tonight.
Thank you. Thank you.
Oh, okay. Oh.
Yeah, cool.
Oh, thank you. Oh.
Right, okay. It's okay. Yeah, it's okay.
Leading in 1, 2, 3, smile.
Okay, thank you.
Thank you so much.
very much.
Thank you very much.
I have one more question.
Yes.
Okay. Yes.
I understand that your size is very complicated. So when we are an engineer, so
Yes.
when consider the structurally integrity. So is it very difficult to convince the structural engineers how do they calculate it? And prove your facade is structurally sound and safe is very, very difficult. I think your facade is very complicated. As maybe as an engineer, I think it's very difficult to prove it's sound safety, structurally sound safety.
There are two steps to the engineering process. One is the initial pre-check. Again, going through the cycles of design, the initial pre-check, can you check for me something? And they will tell you, okay, I require 1 month. And it's like, you don't have 1 month. You have 2 days to tell me this size is correct or not. Because I need to plug this to a system designer, that plug it to the 3D designer, and then I get to the architect. You cannot go linear. Yeah. I cannot give you all the information, so you do your 2 months to calculate and create a report. You need to be able to be agile. That is why the 3D enters here. Once most of the engineering work was not done engineering calculating stuff, was coordinated with us, that the 3D has the information that they require to be able to plug it in our case, we're using Strand 7 and their own scripts. So then they can run their own calculations. So they spend the initial calculation, the initial communication time with the design to make sure that the 3D could do that work in the future where, let's say like this, press a button and you get a result, more or less quick, which was not the case because it's way more complex. And something to show as an example is this page that the engineer used to show us. This is every single rod. So it was a finite element. So when the client say, I want to make the window a little bit bigger. Okay, so now this panel is getting extra load because now this tension rod is longer. We do an update in the model and automatically you have an utilization here. This bar here that was shown by our engineers sometimes was automatically updated and it tells us which is the utilization. To do that kind of redo in that kind of geometry, we only need to update the 3D, move that to the right, they run it. It's not like press one button one day, but it's literally...
it takes many months, but yeah, but the end goal
Go to that point, it takes many months, but the iteration, the coming back to the client and say, can you move it to the right a little bit more? Run that iteration, it costs way less time. If you work linearly, then that's all. Once you award the project, you need to tell the client, sorry, you cannot change nothing. There is no time for you to give any input. In this way, we can always fine-tuning as we go along because they have easy ways to come back to us and say, yeah, you can move a little bit to the right. Okay, 150. If you move more than 150 to the right, the utilization goes from 60 to 95. More than 95, sorry, I'm not comfortable enough. That was the tool to communicate with us. When they were saying, I'm not comfortable with more than this utilization for this particular element. Or, yeah, no problem. I need to go to the next rod size. Instead of 50 millimeters, I need 80. Now I go to the client and say, yeah, no problem. I can move to the left. But now this, instead of 50, is 80. And the client is like, no. That communication needs to be fast. Otherwise, you can see how many rods there were at the end, 700, 800 rods. Yeah, there were hundreds of rods. They had opinion if every single rod, too big, I cannot see the window. This could be fast, otherwise 100 years to finish a project like this.
Yeah, but I think one sentence, like the engineer is really capable of, doing this kind of data management and scripting that makes it make it work. Yeah, so I think it is, true boss is the engineer in this project.
Yeah.
Okay. So anyway, we are running a bit overrun, but I think we have one more question online.
Yes.
From 𝗥𝗲𝗍𝗆. So I think she said the glass panel in the model is very distinct from each other. It's challenging to put them in correct sequence on the side from the curved and irregular surface. Assembly work like putting many and different pieces in a puzzle. So how can the team ensure the correct assembly of different and many prefabricated glass panel on the site by those workers? Because those workers, they are not really understand our design. Right?
I think the first answer is, again, we have a naming system for the glass, and this naming system carry through the very initial stage. So we know this class is number 1, this class is number 2, and etc. here. And from here, we can easily generate diagrams, even if they don't read 3D models. We can create easy to understand diagrams for installer to install. For example, yeah, of course, many installers, they don't open the Rhino model to pan around to know which one is a rod. But let's go through here. So we can create quick diagrams for them to understand which panel go where in which elevation, which we didn't show in the slides, but we did create some diagrams for the installer to understand.
Yes.
And at the end, I think you can see the kind of GIF that we have for the glass. Let's go quickly. You can see the glass sequence right at the end, and actually it's just an automated screenshots that is basically turning off 1, 2, 3, 4, 5, 6, 7 glass sequence. So basically, I think it is a long answer, but the short answer is we have attributes to our glass surface, and then we find whatever way we can do within that data to represent to different parties.
Yep.
GIF for project managers, diagrams for workers, etc.
Yep.
Great. Thank you very much. So everyone, I think this is conclude our technical sharing section for tonight. So we hope the insight from the 𝗪𝗪𝗍𝗪 Ghana retail has been valuable for your own BIM journeys. So please keep an eye on your email for the CPD certificates details, and we look forward to seeing you in our next training sessions. So safe travel home and have a wonderful evening. So that's all for tonight. Thank you very much.
Thank you.
Thank you.